Okay, let's get started. Yeah, last week we mainly combined the path diagram and the factor models, and we have general SEM model. And a very simple case, a very simple example is a mimic model. Okay, we only consider one factor in that case, and we have multiple causes. Okay, we have in our example we have age, EDU, or gender, or whatever, some causes, and then we have some indicators for that different factor, which is reasoning ability. Okay, so which is called a mimic model. And we have that lab, and then we use a factor model to reanalyze the MTMM table. Okay, so we have multiple methods, we have multiple traits. We use a five-factor model to analyze the all data. Okay, and this week we're gonna look at some modifications. So in your homework, okay, homework 3 and 4. Homework 3 is for EFA, that's good. For homework 4, actually the model fit is not good. So if you answer the model fit is good, actually it's not quite
But last year you said even though some of the indicators may be positive and some negative, it depends upon the researcher in order to choose.
Exactly. Generally, you should have some
reasoning.
Some reasonable values for some. Not in that case. I think the NFI or NFI, CFI, they are kind of like a 0.8 something.
They're
which
really
is
close.
Lower than 0.9. So that is not good model fit. So today we're gonna see some model modification, trying to improve our model.
Okay.
And with the software will provide a lot of suggestions. How are we going to consider those suggestions and improve the model fit? And the session 2, so we're gonna consider the mean structure. So far, we didn't talk about the mean structure. We just look at the covariance part. So we talk a lot about the sigma, capital sigma. Capital sigma is a model-based covariance matrix. And then we're gonna add another component into the SEM, which is mean structure. Okay, so we have some estimation, we have some examples. I don't think that we can cover this part today. If we don't have enough time, we can just continue next week. Okay, but before we have these new topics, we're gonna say something about homework. Yeah, homework 3 and 4 are for the same data set. We have EFA and CFA. Suppose we're supposed to explain them this week, but because of the data set is late, so I'm still waiting for some student submission. So we will talk about homework 3 and 4 next week, okay? So until all of you submitted your homework. And
if we've submitted it, can we go ahead and make edits?
Yeah,
now that we know that it's not a good model.
Right?
You can read, we can read something, that's good, okay. And we can also look at some updates of our syllabus because we have some change in our schedule. So let me show you the syllabus. Okay. So previously we have. Let me go to the schedule, the course schedule.
Right there.
Here. So previously we have presentation on April 25th. But because of the conference, okay, so in the beginning of this semester, this conference is an educational area. Okay, they said it's a Zoom meeting, so we don't have any schedule for that. But they said, okay, now because the pandemic is almost over, so they decided to have an in-person meeting. So I will go to attend that meeting. So on April 21st, no class, but that is our presentation day. So we don't have the actual meeting. Please record your presentation. How many minutes? I will send an email. So maybe within 10 minutes or I don't know. Yeah, maybe within 15 minutes. And then please upload your presentation to ELT, and I will just read your recording. I will just listen to your recordings and then give some feedback and scores to you. So no class on that day, okay, no class on 20, April 25th. And of course, on May 2nd, it's a reading day, so we don't have any class. And the final paper will be due on May 9th. Of course, all the submissions are welcome. Okay, so we have last meeting class on April 18th. Okay.
Wow.
April 18th is Q&A. So if you have any question about your homework, about your course project, if you want to resubmit your homework, yeah, that's okay. And if you have any question about your course project, yeah, just bring your questions on that day. And yeah, that's it. Yeah, this is a change. This is the update in our Swift. So any question? So basically, just record your presentation and send it, upload it to ELC. And we don't have any physical, yeah.
Have you posted the outlined assignment
yet.
for?
Yeah, not yet, but
So that way we can get,
okay, good. Okay,
because we need to know what it is before we have questions on it.
yeah, it's just like the all
Last
one of
semester.
the previous SEM one, but yeah, I will do that. So, okay, thank you for your reminder. Yeah,
Sorry.
that's it. And the last day, so the May 9th will be the last day. Okay, so you have to submit everything before that day. You can give me the course project maybe earlier, and the homework is of course earlier. Yeah, but after that day, I will not accept anything from you. Yeah, that's it. And so let's look at our today's class. Section 1 about the model modification. So just like our homework 4, okay, many times when we have a model and when we have very reasonable kind of like, okay, specification or explanation of the results, but we found that the model fit, actually, model fit indexes are not quite good. So when you talk about the evaluation, you should fix that part. Okay, you should tell people that we are going to improve that model a little bit. Okay? So modify, improve your model. Yeah.
So on the model modification, would this be after we do like a pilot study or a pilot test? Like if we did a small sample size before we did our giant one?
Always have some
The
problems.
30, right.
Even though, okay, the full model is really good, but if you only have some very limited number of the sample size, you may have this problem, that problem. Yeah, we have some. So I don't know if, yeah.
So for my dissertation, we're looking at doing a pilot study of 30 to 50 samples
I know.
before we do the giant one.
You
So-
can try to, yeah, you can try those first, but cannot guarantee that
Okay.
the problems will.
Thank you.
So model evaluation evaluates possible ways to improve the current model. Okay. And what should we do? We just remove some paths, or we can add actual constraint. So if we think that this path is not reasonable, then we can just remove that. And the software will just report what's a change in our model fit, because you do some adding or removing or some actions. So they will do the comparison for the current model and the model after we done the change. Okay. And of course, this is not a perfect method. Okay, the method should be used with caution. Of course, you have to understand the meaning of the change. You cannot just add an unreasonable path or just remove very important path from the previous one. Okay. So the theoretical framework is almost very, very important. Okay. Let's look at all the data. We use active data, so advanced cognitive training for independent and elderly data set. We use it a lot of times. Suppose we have 3 cognitive abilities. Okay, memory ability, reason ability, speed ability, and we have some variables available for the mediation analysis last week, not last semester. So this is one of our models for the data set described before. So use the same data, we're gonna try the mimic model again. Okay, so we add a reasonable latent factor for this LS, WS, LS, LT indicators. These are three tests for reasonability. So, and of course, the HDLTT is for memorability. So we don't need to add a latent factor because there's only one test. There's no need to add a latent factor. So we just add one R. So the path diagram, actually, I created path diagram last class. Let's do it again. So just like this one. So we have these two, and yeah, I don't want to repeat here. So we only need to add inability here. Okay, and we have three indicators. Sorry. So let me just draw a new one. So that memorability and we have Visibility has three indicators. Okay, we have WS, we have LS, we have LT, and we have EPT, which is our internet our and we have the covariance, Plus we have the residual part, okay, residual part, so you can see the output. Mediation, these are latent variables here. This is a latent variable. And we have some mediation here from here to here, and from here. And then we have direct effect. And from here to reasonability, direct effect. From here to here. Has indirect. So this is a code. Okay, if we use M plus, that's it. So let's just compare this code and the path diagram here. The variable, these are variables, and the model, okay, R by these three, okay, R here. By, before by, this is the latent factor. We just newly created a variable called R. So by using by, it's generating a variable R here. And the WS here. So we use a star here. So that means the factor loading will be really estimated. So we have lambda value here. We will have lambda value here. It's not fixed at 1 because we freed this factor loading here. WS and LT here. And as a variance, instead, okay, so instead of fixing the factor loading at 1, so we fix the variance of the R at 1. So this is the model identification. We free this parameter, we fix this variance of R at 1. And R on H and ED, okay, R is regress on this value, and also R is regress on this value. Okay, 2 causes. HDLTT also, okay, is regressed on this value, okay, and is regressed on this value. So we have 2 causes for HDLTT. And the EPT okay, on H, okay, on H, this path, on EDU, this path, on R, this path, on HDLTT. Okay, so we have 4 causes for EPT. One of these will influence the EPT scores. And we have the mediation effects. Okay, so model indirect, that means we have the mediation effects. So EPT, IND, EDU, okay, EDUs here. So all the indirect effect from EDU to EPT will be reported. Okay, so we may have this path, we may have this path, indirect effect. So we will repeat, and also EPT, INTH. So all indirect effects from H to EPT will be reported. So we may have this path or this path. This is a code, M+ code. So let's try to do that. Okay, so we can look at the result, output. I submitted the code, so maybe I didn't submit the code. So go to the LC. So it's input file modification. Okay, modification. So we can open the M+ in our desktop and open the code and download the code and open the code modification. Oh, the data set, okay, active and plus, so active. Right, there's a one, so please just it's called active M+ .txt. That is our data and just the same code that we shown in the slides.
Is this an eye exam?
So we have title, data, variable. So only these variables. Model R by these three are fixed one. That's it. Yeah. So this is our model. So you can actually in the first you can just try. And using this symbol, this is a comment. Okay, so in the very beginning, we don't care about the modification, just run. Errors. The data file cannot be found. Okay, so I think that the data file is not here. save the data in another folder, so that's why I cannot find the data file. Try now it's working. Okay, so let's look at the results. Okay, so let's look at the results. We have the input instruction here and data information, variables, all of these variables, and the algorithm, and this descriptive statistics, and the model fit. Okay, now let's look at the model fit. Actually, it's not good. Okay, so the RMSEA is more than 0.1, and the TLI is less than 0.9. And this one, which is SRMR, also is quite large, larger than 0.1. So the results are reported here. The model results are reported in this table. So we have the lambda, these three lambda, okay, factor loadings. Lambda for WS, lambda for LS, lambda for LT. And we have the coefficients. Those are coefficients, regression coefficients. And yeah. So this is also coefficients. All of these, okay. Coefficients for EPT, for R, HVLTT. And we also have the mean part. So yeah, just ignore the mean part, intercept. And then we have the residual variance. Okay, so R, the variance of the variance of R is fixed at 1. But these are residual variances. Okay, so we have memory test. We have 3 reasoning tests. We have EPT. Those are variance. Those are just residual variance here. For EPT, the variance of the residual part, and the variance of the 3 indicators, residual for this, and also residual for HVLT. Okay, so we have 5. We have 5 residual variance. These are recorded here. We test, reasoning test, the dependent variable, the memory test. And we have the mediation analysis. Okay, so the next part is about total indirect, specific indirect, and direct effects. So all the mediation model related results are reported in this part. So for example, this is effects from EDU to EPT. Okay, so this part is from EDU to EPT. So from EDU to EPT, so all the direct and indirect are listed here. For example, the total is, this is the sum of direct and indirect. Okay, this is the sum. And among these, okay, the total we have 0.553 is the total indirect. The next part is the difference between these two is the total direct. Okay. But the total direct is here. This is a direct. This number add this number is 0.948. Okay. 0.553 add 0.395 is 0.948. Okay. And among the total indirect, we have 2 specific indirect. One is 0.087, which is from EDU through HVLTT to EPT. So this test through HVLTT to EPT, this indirect test is 0.087. Okay, the product of these two tests is 0.087. And another specific indirect from EDU to R through R to EPT. So it is so EDU through R to EPT. So which is a product of this test and this test. Product of this test and this test. So this is 0.466. Okay, so this is 0.466. And add these two numbers together, we have the total indirect. Okay, add 0.087 and 0.466 is 0.553. So this is the indirect from EDU to EPT, and the same thing. The next part is from H to EPT. Okay, so we have total indirect, we have specific indirect 1, specific indirect 2, and the total effect. All of these are reported here. Now let's look at the significance. The direct from H to EPT is not significant. Okay, so what should we interpret the result here? So this one is not significant. This is a direct. This is direct from H to EPT. Okay, from H to EPT. So it's this path. It's not significant. This path is not significant.
So would you remove that one?
That's the next step.
Okay,
Yeah.
sorry.
So far, yeah, just look at the previous analysis.
Right.
Suppose we don't know about the animal.
Yes,
So
ma'am.
this one is not significant. So how are you to do the interpretation? So let me ask you, is that complete mediation or partial mediation for HVLT? Based on the result here, this
Well,
number, which is larger than 0.05. Suppose that 0.05 is alpha level, then direct from H to EPT, this path is not significant. So let me ask you, is partial mediation or the complete mediation?
Complete.
Why it's complete?
Because right when you added in the mediator, that the significance between.
Exactly, because it's gone, the mediation effect, not the significance is gone by adding the HVLT. So it's because of this mediator, we have not significant results. So this is the complete. Now, how about this test? Let's check the previous.
So this would be similar to, so the Cronbike alpha score is for the construct itself, while this score is for the actual between the both, correct? Is that making?
Cronbach alpha?
Yeah, the Cronbike alpha that we did a couple weeks ago is for the construct itself. So this would be checking,
No,
it
it's
reinforces it? No?
different. No, it's different. No.
Okay.
No. Yeah.
All right.
So let's look at the direct effect from EDU to EPT. Okay, direct effect from EDU to EPT, which is this test from EDU to EPT. This test. Let's look at the result here. I'm sorry, this is so messy. So let's look at this value. Is that significant or not? Okay, this is significant. So what does that mean? It's partial and it's significant. Okay, so from here to here. Okay, so this is the result we obtained from the, and all of these are significant. Okay, specific indirect. This is significant. This is significant. This is significant. No, not this. Okay. Specific. Yeah. So what does that mean? So this one. The mediation effect from here to here, this is significant. And also this is significant. And also this is significant and this is significant. So there is a mediation effect. So HVLTT and R, the reasonability actually mediated the effects from H or EDU to EPT, okay? Because all of these are recorded as less than 0.05, they are significant. So we have some conclusions. Okay, so from H to EPT, it's not significant. So So that's why it's complete mediation. Okay, it's complete mediated by the HBLTT. HBLTT is on top. Okay, it's completed mediated by the reasoning ability HBLTT test here. And here and here. It's negative, so let me check let's check the result here. From H. Yeah, the total indirect is negative, and all of these are negative. It's significant. So the negative relationship between H and APT. So also check the total. Okay, it's negative. It's significant. By the memory ability HBLTT. Okay. And the reasonability, both, because in that case we have two mediators. One is HBLTT and the other one is reasonability R. We have two mediators, okay, by these two. Because both indirect effects from H to HBLTT to EPT and from R to EPT. Okay, so it's here we have some notation, and if we use A and B, so that means we have some notations. Yeah, in the next slide, we have a detailed path notation from each. So it's A here, it's B here, and the B edge, it's B here, H here. So we have the detailed name. So all of these are significant. Okay. So they are significant while the direct effect is not significant. Yeah, let's try to use R to specifically look at the name of this path. In M class, we don't need to care about the name of this path. And from EDU to EPT, EDU education to EPT, it's significant. Okay, so it's and also it's positive. So if we have the result here from education, it is positive. Okay? Total indirect, all of these are positive. The higher level of the education you have, the stronger the EPT scores. Okay, so that's good. And for age, the older people is, then the lower score of the EPT. And it's partially mediated because the direct effect is significant, so it's partial mediation. Okay. And of course, we have two mediators in this case. Now let's check the model modification. So this part is done. This is the result part. But if you go back to the model fit indexes, so we have some values reported in the beginning part here. Okay. Here, model fit information. Suppose you forgot the EIC-PIC because EIC-PIC is a model comparison. So now we don't care about two models comparison. We just look at the model evaluation, the current models evaluation. So we have square value here, freedom here, P value significant, RMSEA here. Let me just copy this part. Let me just copy the result. And we can just look at the slides. This is our result.
Break it down into two columns and it'll make it easier also.
So Yeah, so we have analytical value, CBNC, Pascal value, freedom P value, RMSE, CLI here, PLI here, and the SRMR. So you can just fill out this space, answer all of these numbers here. So overall, it does not fit the data quite well. Actually, yeah, this question is this model a good model or not? It's not. Because this number is quite large, it's so large. Yeah. Even the lower bound of 90% of confidence interval is much larger than 0.05, even 0.08. So that's not a good model. Then we're gonna see some improvement. Okay. Yeah, before we move forward to the actual improvement, let's just look at some theoretical concepts. Okay, because we're gonna use some chi-square difference test. We're gonna look at the Lagrange multiplier test. We're gonna look at some word tests. So first, let's try to look at the nested models. What are nested models? This is just one of our possible models. And actually, we have some other possible models. We're gonna change the current model a little bit, to use other possible models and do model comparison. So, nested model. Suppose we have model complexity bar, and this is maybe the most complex, okay, most complex model. And maybe this is the most simple model, the simplest model. So here we have independent model, okay, independent model. This is very simple. So in this case, we don't have any association among them. So suppose we have three variables are just independent. So this is very simple. Okay, we don't have any association. We don't have any relationship among these variables. And the saturated model, okay, so suppose, okay, so all these variables are correlated, okay. So suppose we have the model with each pair of the variables associated, okay, related. We have those complete ones. Among them, we have some possible models. For example, here, model 1 is between these two extreme models. And here we have model 2. We have, this is another possible model between these two extreme cases. Then if we, okay, so here, starting from here to here, if we put some constraints, okay, that means, okay, we fix some parameters, or we can make it 0, we can make it the path 0, or we can put some constraint on this model and we divide the model 2. The model 2 is simpler than the model 1, okay, because model 1 is closer to the complex model. Model 2 is closer to the simple model. So suppose from here to here, we can derive the model 2 by adding some constraint on model 1. Then we say that model 2 is nested within model 1. So what does that mean? We can obtain the singular model by putting some constraint, for example, fixing some path or fix some values at some fixed value. Okay, so or we remove some path. And then we have the similar model. So we can say that the model 2 is nested within model 1. Okay? They are nested with each other. very simple case. Suppose we have three variables here. So suppose we have, this case. And this is our model one. If I assume this path is zero, okay, assume from here to here that the coefficient is zero, then actually it just means that we're gonna remove the coefficient from here to here because we assume there's no relationship between these two variables. Then the model two, the singular model is nested within the previous model with this existing. Okay. And the independent model, we just remove everything. Okay, so all these are removed. Okay, put all of these constraints, make it 0, 0, 0. Then we have the independent model. Okay. So based on that complexity bar, we have different tests. Okay, so for model tests, we have different ways to do that. For chi-square difference test is for nested model. Okay, we use the likelihood ratio test. In last semester, SEM1, we also mentioned the likelihood ratio test. Basically, we're gonna use two models. Okay, one is called model 2, the other one is called reduced model 1. So suppose here we use different names. Okay, so whole model is more complex. In this case, the model 2 is here. Reduced model, the singular model is model 1. So here is model 1. In this case, then the model 1 is nested with the model 2. The model 2 is called a full model. It's more complex model. Model 1 is singular model is called reduced model. The simplified model. We have two models and we're gonna do the comparison. Based on what? Based on their chi-square value. Okay, so for each model, we're gonna report their chi-square value. And then we get both chi-square values and also we obtain the degrees freedom. So the difference in their chi-square value with that degrees freedom, the difference among these two models will be compared with the critical value of the chi-square distribution because we assume the difference follow a chi-square distribution. Is the degrees freedom is just the difference of the degrees freedom among these two models. Okay. And we compare the difference between these two models. So this is a detailed technique. Okay, if significant. So what does that mean? If significant, choose M2. So what does that mean? Significant. So that means the model 1 here, the model 1 reduced model is significantly worse than the model 2. Model 2 is the full model, is more complex model. Model 1 is a reduced model. After we put some constraint, we have a new model here. This model is significantly worse than the full model. A reduced model is always worse than a full model. It's always worse than full model. But is that significantly worse or not? So the significant tell us if the reduction or we have some constraint, if the change will have significant change or not. Okay, so the reduced model is always worse than the full model, but if that significant or not, if it is significant, that means okay, then this model is not good because it's dramatically worse than the full model. So we're gonna use the original model. We're gonna use a model, the more complex model.
But what about the saturated model?
Saturated model is also one of these. Okay, yeah. So
Sorry.
usually it's a full model, saturated model. Usually the model fit is perfect. When you look at the chi-square, it
Zero.
didn't report because it's perfect. No degrees freedom available. So if this one is significant by running the chi-square difference test, then we're gonna discard the model 1, the reduced model. We're gonna keep the model 2. Model 2 is much better than the reduced model. Otherwise, what does that mean? It is worse than the model 2, but it is not significantly worse. But model 2 has fewer number of parameters. It's much simpler. It's easier for us to do the interpretation. So we're gonna take model 1. Okay. Otherwise, if it's not significant, we're gonna use the similar model. That's a theory, okay, for the high-school difference test. That's one test. We can also use a Lagrange multiplier test. So as I described before in this slide, okay, so I'm sorry. So in this slide, so when we have this, when we have this bar here, so this is the most extreme case here. This is also the most extreme case here. So we start from, for Lagrange multiplier test, we start from a reduced model. We start from a similar model. In this case, it's model 1. And then we try to add some path, okay? Start from a similar one, and we try to add more path into the current model to make it more complicated. And then we will have the Lagrange test, okay? And this is also widely used in our computer software. I think that the M+ or the by default R uses the kind of test for model modification. So what does that mean? So for model modification, they will try to add some possible models of some possible paths for you, and then do the comparison, okay, to test if that's significant or not. And we have another one called a word test. Okay, starting from the more complex model, model 2, we start from this model and try to reduce, try to delete, try to remove some path from the complex model. Okay. And then we compare these two models. Okay. We will use these two tests in our example. So we will do all of these tests. So in M+, previously we showed that model fit is not good. Now let's try to add something here. Okay, in the output, model indexes. Okay, model indexes. And now some number 10 here. So I will explain what does that mean. So what is this? So in model in the indexes actually tell us that I'm gonna do some change. I'm gonna add something. So that is actually the Lagrange multiply test. I would like to add some path into the current model to see what's the change in our modification indexes. Okay. So we have some report. We have the model modification indexes, expected parameter change indexes, and we also have some different types of standardized expected parameter change. Okay, that's for standardized parameters. And we have some numbers. So what does that mean? If the indexes change is larger than that number, please show them. Please list all these possible ways. So this kind of give a threshold. If the change is less than, if the model modification index is less than 10, then please ignore those suggestions. Just report the suggestions which will cause a large modification index which is larger than 10. Okay. So this is number. You can just change this number to 100. It doesn't matter. Or 500. It depends on your detailed model. It just thresholds. Okay. So let's just try to run the code. Go back to the M+. Go back to the code here, and then we're gonna release this comment as in the very beginning. So we just log that. Okay. Now I release this model modification statement here. And trying to rerun the code on the code, and everything keeps the same. Okay, same. And then the last part. Okay, so starting from here, after the mediation analysis in the previous result, we just added it here. Okay, that's it. But for modification, we have some actual part. Okay. Model modification indexes. Okay, so these are result for the model modification. Minimum modification index value for printing the model modification. Okay, it's the 10. Okay, so because we give a number 10, by default it's 10. This is the minimal MI value. And then look at this. Okay, these are all suggestions. This suggests to change our model like this way. For example, add a statement with on or by. Okay, so HVLTT on R or R by HVLTT. So what does that mean? So let's look at let's look at the diagram here. Where's the home? See, this is the best diagram. Okay, so the past diagram is like this is our past diagram. And what is the suggestion? HVLTT on R. What does that mean? HVLTT on R. So that is suggestions. That is this one. Okay. It just gives us a possible model trying to add this tag. HVLTT is regressed on R. Okay, HVLTT dependent variable is regressed on R. So R gonna change the HVLTT scores, or R by HVLTT. Okay, R is also measured by the HVLTT. So this is one possible statement by adding on or by. And the change in the modification index will be 180. So that's a lot. That's a lot. Okay. And the expected parameter change. Okay, EPT. Expected. Yeah, EPT. Expected parameter change 1.9. And also we have some standardized EPT. Okay, standardized EPT, this value or standard YX, both X and Y are standardized, and we have this number. So these are another version, two versions of EPT. So we only need to look at this one. So what does that mean? So that means the visibility actually can cause a memory ability. This the reverse maybe makes more sense. Okay, let's look at the other statement. On statement. R on HVLTT. So in this case, it's just a reverse, okay? It's R on HVLTT. So it's this direction, okay? So the same path, but with different direction. So it's HVLT. So that means that memory ability is gonna influence the reading ability. That makes sense, I think, okay? So the people's memory ability is gonna influence the people's reasoning ability. This is the meaning of this statement. On HVLTT. Okay. R reversed on HVLTT. R here is reversed on HVLTT. So this makes sense. And because the same path, okay, because this actually is at the same path, but different directions, so the change of the model, modification indexes is the same, okay? And then the other ones are on EPT. Okay, what does that mean? R is regressed on EPT. So that means we should add this path. This is not reasonable, okay? Because this is the outcome. This is the final outcome. And by taking that piece of suggestion, you actually want to add this path, okay? EPT gonna influence people's, no, this is not reasonable. So we will not take this suggestion. HVLTT on EPT. So this suggestion to add this path, okay? So HVLTT is regressed on the EPT. Does not make any sense because again, this is our dependent variable, okay? So we're gonna look at the inference from here to here. So this is also not reasonable. So we will not take this suggestion. So you need to check each piece of suggestion here and to really understand the meaning of this statement. And then you need to check, okay, is this a really good piece of suggestion or not? Shall we take this suggestion or not? So you need to check the model by understanding the statements here. With statement, okay? HVLTT with R. So it's the same, okay? We're trying to connect these two, but both directions. So with association, okay? So means covariance, we have two variables correlated. So that means we have two directions, but again, I think that this is not good as this piece of suggestion. So we will not take this suggestion. That's it, okay? So this is the other part is diagram information. So basically, these two parts are the same, but with different directions, and I think that this direction will be much better than the first one. So we can just try to add this path, okay? We can try to add this new path into our model. And the model will be much better. So that's a code. And how are we going to do that? Just copy this code, okay? Just copy this code here and rerun the model, okay? R on HVLTT. Okay, so we will. So that's a new code. It's trying to change the model. Yeah, so here, this is the code I will upload. Yeah, I will upload the code. You'll see, this is a new code. The difference is just we add one more statement here, R on HVLTD. We just copy this statement from the output of the previous code. Okay, so R on HVLTD. So that's it. R on HVLTD. This is a new path. So everything is the same, and we have something new. And then we can try to run the code, the new model. First, let's try to look at the modified indexes. Okay, now let's look at the modified indexes. RMSEA this time becomes really slow with 0.034, less than 0.05. And then CFI, TLI, okay, this is really close to 1, 0.997, 0.992. And also SRMR, it's very close to zero, okay? So we can highlight copy results. This is a new model. It becomes much better than the previous one. Okay. So if you want to do the comparison, so this time, MSEA is point of the previous one. The previous one is 0.144. Now it's 0.034. Okay. So it's changed dramatically. And the TLI, the last model is 0.862. Now it's 0.992. And the chi-square value, okay, the previous model, the chi-square value here is given here. Now the chi-square value here, 18.363 and it's freedom 8. So we just add one more pass. So the degree freedom just -1, okay, from 9 to 8. And then the change in the degree freedom is 1, but in change in the chi-square value is huge, okay? So this value is larger than the critical value of the chi-square with 1 degree freedom. It is significant. So this is a reduced model. This is the previous one is a reduced model because here for the model 2, we have one more path. It's more complicated than the previous one. So this is M2. This is a simpler model. This is a reduced model. This is a new model. We have already added one more path. So this model is significantly worse than this model. So we should take model 2. That's one way. Okay, by using the next model, by using the chi-square test, it suggests that we should keep the model 2. We should not use model 1. Also, by looking at the RMSEA, okay, so this one is so large, this number, but here it's so small. And this is really close to 1, but here it's not less than 1. So RMSEA and TLI and also other suggestion, other modified indexes suggest us to take the model 2, okay? SRMR and also TLI. All of these suggest model 2 is much better. So by adding that path, this path, is a better model, much better model. Any question? This is one way we do the model change. Okay. Yeah. Any question? We use a chi-square difference test. We also check the RMS. Actually, we have some other tests.
So when you're writing up, say, your results and conclusions, would you have a whole section talking about the model modification?
Yeah, you can say
And
that. You can say that.
you
can say
justify
that.
why
Originally, we tried that model. Well, you can see that the literature review, the previous research suggests that model, and we collect data. We try to fit the previous model, the old model, traditional model. It doesn't fit well, and then we modify the model by adding or deleting some path, and we have a much better model. So that should be your new theory. In your new model, in your new theory, you think the reasonability is influenced by the memory ability. So the people's memory ability gonna dramatically change the people's reasonability. That is a new theory. But for the previous model, people didn't consider the relationship between these two abilities. So that's not very good model. So yeah, question.
Well, I was just gonna go with this. If we're looking at a model, let's say in literature,
Yeah.
and they just had a factor analysis with two latent variables, but you think that there's like a hierarchical factor analysis, and you add, would that be like a way to do this? You can
Yeah.
look at it that way, like I want to
You
add.
can also do that, yes.
Okay.
Yeah, you can add another higher level factor model, and you think if that fit much better than the
Right.
previous one, you can say, okay, maybe we can think another factor
Mhm.
which gonna govern all of these lower, the lower level factors, something like that.
So for a journal article, we would just talk about in our results and conclusions, but for a dissertation, if we run into this, say I'm proposing model A,
Yeah,
do I have, and I find that the model's wrong, do I have to go all the way back to 1, 2, and 3
Oh,
and
it's-
change model or no?
it's totally up to you. If you have your, if you have your model, you can just have the new model. You don't need to talk about the old model.
Okay.
Yeah.
Okay, thank
Yeah,
you.
yeah.
Good.
Yeah.
I don't want to rewrite it a third time.
Okay. Okay, so we can also put some constraint. For example, based on the previous analysis result, we found that EPT on age actually is not significant. If you check the previous result, we found that this path from age to EPT, this path is not significant. Okay, this path is not significant. Then how about we just remove this path? Okay, I don't want to check the direct inference. How to remove this one? We can just assume the path coefficient is 0. We fix the path coefficient from EPT from age to EPT is 0. Okay, so this one is fixed at 0. So we have this constraint. The coefficient fixed at 0 from age to EPT. This is another possible model. Okay, let's try to look at the model. Then we have something new here. Everything's let's check the code. Everything's the same here. But this one is new. And of course, we also take the suggestion in the previous model. So let's try to, you can also change your code by yourself. Okay, so let me upload the code to. Okay, so here we have some modifications. We have so many, we can ignore some of them. So each step we can try one. Besides, fix the one, fix the 0. This is a new result. After we add the new constraint. Okay, so we have the result here. And then let's check the model fit indexes here. Okay, model fit information, we have chi-square value, okay, degrees freedom. Degrees freedom now is 8, okay, because we deleted that path. So we have the previous model and the modified model, we have 8. Now we have 9 because we removed that path. So we have new degrees freedom. So we have 9. P value and RMSEA is still very low. And these two numbers are still very large, close to 1. So if you do the model chi-square difference test, okay, the difference in the degrees freedom is 1. Previously we have 8, now it's 9, so the change is 1. And also you can check the value, chi-square value, now it's 20.293. The previous, what is the previous result? Let me go back to the previous result is 18 something. Okay, so this one. 18. Let me check, yeah. 18.363. By adding this statement, by removing the path, we have the chi-square value is let's see, the value 20.293. So the difference is less than 2. Okay, the degrees freedom 1. Okay, check the chi-square distribution with 1 degrees freedom is 4.84. Okay, which is less than the critical value. So it is not significant. Not significant. What does that mean? We should take this model because this is similar model. This model is the model by adding this path and also remove this path. Okay, so by compare the model with and without the path here, there's a change. The difference is not significant. But without the path here, it's much simpler. So we should use the model without this path. It's because it's not significant. Okay, you can just totally ignore this path to make it simple. And the change is not significant. Okay, it also suggests that we should use model without the direct effect from H to PT. And if you check the other model fit indexes, these are really good. Okay, is very small, and also these two numbers are close to 1. So SRMR is very close to 0. Okay. So we should use a new model. It's called word test. Okay. So based on the previous model, we try to delete, we try to remove something, okay, from the current model. So it's called a word test. Word test. So EPT on age, which is not significant path, we can totally make it 0. Okay? Make the path 0. So we have the class code here. Yeah, you can just release these comments. Sorry, I give you too many options here. Those are options for you. Suppose you want to release this comment, okay, EPT on age, and we define that the path, the name P, it is not significant. So we try to do the word test by adding this part. Okay, so the P, the path here, I'm gonna do the test. It is 0 or not. Okay. First, we can just this is makes so complicated because I combine several models together. Let's try to look at that. Yeah, this model is similar, so I'm trying to use a model described here. Okay. Ward C, because ward is a combination of several models and it's so complicated. So the ward C is that we just add this new statement. So the original one, P on H. Give you several models. All of these are ward tests. So let's try to run the code here. So this is actually the result. We first manually did the calculation. Okay, the change of the degrees freedom is 1. Okay, the change of the chi-square value is 0.9 because the original is 20. Now the next time is 18 point something. The change in the chi-square value is 1.931. But if you add the statement of model test, okay, so just ignore this statement because these are for comments. If you add a model test, this is for water test, the P is here. What does that mean? Which one is P? P is here. PPT on H. Okay, PPT on H. I assume that the name is called P. Okay, so. So this is a code we input. Yeah, EPT on H. The path, the name of the path is called P. And I want to test a path if it's 0 or not. Model test. If this is 0 or not. In that way, okay, I'm gonna test if this path is 0 or not from H to EPT. And the result tells us that this is the result. Here, water test. Okay, now we have conducted the water test on parameter constraint. The change in the chi-square value is 1.9. Degrees freedom change 1. P-value is larger than 0.05. So it is not significant. It is not significant. What does that mean? We should take the model with this path. Okay, without this path. Okay, that is similar model. Similar model because the test is not significant. We should use a reduced model by assuming that path is 0. Okay, the coefficient is 0. Yeah, so this is a word test result output. This, the previous part is for EPT on H. We can also change to another word test. R on H. So let's see P1. Which one is P1? So let's see. This is the code for the word test. And P1, let's look at the code. P1 is R on H. R on H is the name is called P1. Now let's do the test. If P1 is 0, so R on H is here. This path, we're gonna test if this path is 0 or not. Of course, you can also test if this one is 0 or not. You can test all of this. Okay, suppose I'm interested in this test. I'm sorry, it's R on H. I'm sorry, this not this one. It's this one. R on H, this one. If this one is significant enough, if I assume the coefficient is 0 here, then should we have a significant difference among these two models or not? So the name, okay, it's called RP1. P1, it's R on H. This test. And I'm gonna run a word test, model test based on P1. If this one is 0 or not, then just run the code. So the class code. This time is H. P1 is 0 or not. This is another way. Yeah, I use a lot of comments here because you can pick whatever you want. You can make some of them available. So this time I'm gonna test P1. The last model I test P. So this time I put a comment on this statement because I don't care about P this time. I'm going to test P1. Where's P1? P1 described here. P1, this is P1. And then the P, I have already, because I have already done this part, so make it a comment. I don't care about the P. So this time I'm gonna check P1. So, which actually is significant. So let's check the significance change. This is a model. Okay, so now the word test result. The change in the chi-square value is 60.779. The degrees freedom change is 1 because we just then this path only. Okay. Then the p-value is significant. So what does that mean? If I assume this path is 0, P1, okay, then the change in the model will be significant. So what does that mean? This is important path. We cannot remove that one. Okay, suppose this is P1. By assuming, if we assume it's 0, in other words, we're gonna remove this path. And then we did the comparison between the model with this path and the model without this path, okay? Or P1 is 0 or P1 is not 0. So the result tells us the change is significant, the p-value is significant. The value is 60.779, the degrees freedom change is 1. So the change is significant, so what does that mean? So if you remove this path, the model will be dramatically different. Significantly worse, so the model without this path is significantly worse than the model with this path. So we should keep this path. It cannot be removed. Otherwise, the model will be significantly worse. Okay. So the final conclusion, because it's significant, we should use a full model, more complicated model, but assuming this is not zero, okay? So we should keep this path. This is a not much better model. If you remove that path, that will be dramatically worse, significantly worse. We should keep this one. Okay. That is a board test. So how to modify your model? That one, no. That one you cannot remove. But this one, if you want to remove this one, yeah, that's doable. Okay, let's make the model much simpler. So this is a word test. Or P1, yeah. So yeah, we just covered the different tests: chi-square test, Lagrange multiplier test, and word test. And do a lot of comparisons of different models. Yeah, do you want to do some lab, or do you want to do it after class? Maybe we can do it at home. Okay. We can try to change all of these paths. Yeah, just test each of these possible paths here and do the model test. To see if that is significantly changed or not. We can test maybe you can do this test, okay, because this is significant. Okay, so based on the result of the mediation analysis, we know that this one is significant. We totally cannot remove this guy. But suppose we make it zero, removing that one, then what happens? Okay, so from EDU to EPT, well, this one, EDU to EPT, EDU to EPT. So we should modify the MPS code a little bit. EDU to should do here. We should modify the code. This. So suppose it's called a P2. We want to check. Look at the P2. P2 0 or not. So now it's P2. Here. Why the P should go to comments. Now let's try to run the code. This is the result. Okay, this is significant. Okay, this is the result from the water test. Water test, the change in the chi-square value is 72.601. And because freedom change is 1, the change is significant. P-value is significant. That means P1 is important. We should not remove P1. Oh, I'm sorry, P2. I'm sorry. P2, the P2 described here. Okay, so we're gonna test P2 here for this step. P2 described here. EPTRA. I'm sorry, EPTR EDU. Okay, yeah. P2 is EPTR EDU. So EPTR EDU. This path. This path is important. If you remove this path, then the model will significantly worse. Okay, this is also important. This path. If you remove this path by considering the coefficient at 0, then the model will dramatically significantly worse. So we should not remove this path. I mean, you can do a lot. Okay, you can just you can do a lot of other change. See if we support your assumption or not. Okay, so that's for the modification. Any question? Any question? So basically, you just use a model modification, and after you got a lot of pieces suggestions, you just follow each statement and then to understand the meaning of that statement, and think about that. Okay, shall we change the model that way or this way or the other way? And you can also do the multiply test or word test to see if the model changes significant or not. Yeah. Question? Good. Okay. So you can see that by changing some tests, the model fit indexes is much better. Yeah. So most of them fit the model much better. Yeah. Okay. So that's for session 1. If we don't have any question, we can have a 15 minutes break. And next session is for the main part. Yeah. Great. That's it.
So what I was trying to ask about the crown bike alpha was,
Yeah, this is different concept for
Well, no,
from
like-
alpha. Yeah.
so one of those boxes, the observe,
Yeah.
has different variables that would fall underneath it that make that variable.
Yeah.
And the crown bike alpha, if I'm correct,
Yeah.
tells you how those items score in
Yeah.
that construct. Correct? Okay.
Yeah.
And then what we were doing was between the two constructs, the score. So
Uh-huh.
you've got an individual and then you've got a score on the path, the model.
But alpha is only for measurement model.
Okay.
But SEM, we have a lot of regression
Right.
coefficients.
Okay.
Yeah, from the Harvard, just look at the items, the correlations among items, item 1, 2, 3. Okay, so we have 1, 2, 3. So the correlations, and then take the average of the off-diagonal elements, which is our correlations, the average, and then times the number of suppose we have J items, then J squared
Or I,
Those-
or
yeah.
any of those.
divided by the total of the sum of these. Yeah. So it's a full measurement model,
I'm
but
just
not
trying to,
for this.
yeah, I'm just trying to figure out what all I need to score everything. So I'm just.
Yeah, it's
Yeah.
different. Yeah.
Hold on. Thank you.
Thank you.
Have you seen this book?
So wait, it should be, yeah.
So I just got this from Amazon. This was recommended by 2 of the faculty over in Cornell.
And you're gonna read it by yourself?
Yeah.
Oh,
But thumb through it. There's some really cool stuff in there where it talks about the
yeah,
different,
I don't know
how to make
about,
surveys, and
that should be very interesting book.
because a lot of it's method stuff of what you like doing.
Item writing, so that involves a lot because it's about.
How to build,
Yeah, that
design and
that
making.
involves a lot of factors, yeah. Oh, development of response skills, yeah, 5 or 4.
Yeah.
Oh my goodness, that's a lot.
There's a lot in there. I'm literally going through it for
Yeah.
writing my methods 3 and my lit review. I'm pulling a lot out of it because it's got a lot of information in it.
Yeah.
And it's walk step by step. Because most of my stuff is all going to be survey.
Yeah,
survey or
I
interview.
don't know about this survey part, so how to write an item, so there's some guidelines.
Yeah. Well, because all this data comes from somewhere. You know, someone did a survey.
Yes, yes. Language, and also you need to pay attention to audience, oh my goodness.
Yeah. Talks about
Structures,
biases, structures, yep.
That's a lot.
So it even gets into the constructs, it defines the construct, it defines the value, the variables. I mean, it's some,
Oh my goodness.
you know, shit. So it's really cool because stuff you wouldn't think is defined.
Very complex. Very
Yeah.
complicated.
So, let's see, I think that's still it. So, you know, gives you examples and everything. Response, good. There you go. So it even talks about going all the way down to
Yeah.
defining what a construct is, what a variable is, what a value is, you know. So that's pretty, well, I mean,
You should take a course about this.
well, and
survey.
that's what they were saying. They said there's a course here
Yeah,
in,
take that course.
yeah, so
What's the course name?
I don't know. They're the ones that said it.
Actually, years ago, there was a professor teaching the survey, but yeah, he. Okay, section 2 is about mean structure. Okay. Yeah, we haven't talked about sample means. Okay, we just focus on sample covariance. Now we want to so this is a review. Okay, so this is a review. So for data part, we have sample-based covariance matrix. We use S to show that. For model part, we have model-based covariance matrix. We use capital sigma to show it. Okay, so we try to make these two. We try to make this the residual matrix between these two as small as possible. Okay, of course, a model-based is a function. The capital sigma is a function of some unknown parameters data. Okay, so inside of this data, we may have some coefficients, we may have some variance or covariance, but all of these are elements inside the model-based covariance matrix. We have function, and finally we have model-based covariance matrix. This is a sample part. This is a data part. This is a model part, and try to make them as close as possible. Yeah, minimize the difference between these two matrices. That's for estimation. Okay. And previously, we just have these three equations for SEM model. Okay, so we have X, the measurement model, Y, measurement model. Okay, this is a factor model. This is another factor model. We have the structure model by focusing on the latent dependent variable and the latent independent variables. By assuming, all of these three equations assume that the intercept, the mean part is 0. Okay, we don't have the tau x, we don't have tau y, we don't have the alpha here. But if we consider a full SEM, we need to look at the mean in addition to the covariance part. Okay, but the focus of the SEM still the covariance. The main part is not our focus. It's not as important as the covariance part. But in some cases, we need to investigate the mean. For example, we will try to look at the change of the pattern. We try to estimate the factor means or compare means or multiple scores, then we can do the mean analysis. In that case, we have some means, tau x. For x, this is the mean part of x, tau y, the mean part of y, and we have alpha, the mean part of the eta. So in this case, we include the mean. And the procedure, okay, so as mentioned, actually it's quite as similar as the we done before for the covariance part. This time we have two parts. Okay, we have sample covariance matrix S, and also we have sample mean. Okay, suppose we have sample and the mean is N. Then we have two parts. Okay, S and N for the data. Okay, and for model we also have two parts. We have model-based covariance matrix we described before. Okay, so kappa sigma of data. We also have model-based mean. Okay, model implied mean. We use mu. Okay, it's another function of unknown parameters data. Okay, this is a model-based mean. This is a sample-based mean. Okay, then we have four components. And the goal of the model estimation is the same. We're trying to minimize the difference between the sample part and the model part. Okay. So how to do the minimization? We have a lot of like description function. One of them, the most popular one, is F based on maximum likelihood estimation. Okay, so FML is the most popular description function. What is that? It should be looks familiar for you. Okay, look at the first part. This from here to here. This is about the covariance part. Covariance part. Log, the determinant of the model-based covariance matrix, kappa sigma here. Add the trace of the product of these two matrices. Okay. The first part is the sample covariance matrix, and then the second part is the inverse of the model-based covariance matrix. And the product of these two get the trace. Trace is the sum of the diagonal elements, okay? And then log, minus log, the determinant of the sample-based covariance matrix. And also minus p, okay? P is the dimension of the model, okay? The number of variables in this model. This is the covariance part. Now we add the mean part. This is the mean part. Mean part. We have the sample mean, okay, M here. We have the model-based mean. The difference between these two vectors, this should be vectors, okay. The difference between these two vectors, and then transpose. This is a vector, transpose becomes a row vector. It's a row vector now. And then we have the model-based covariance matrix inverse, okay, inverse of the kappa sigma. And then this is the same part here, the mean, the sample mean here, this is a model mean, and then the difference, this is a column vector, okay. So row vector times the matrix here, then the column vector, finally we have one number, okay, because this is a number, this is scalar, the final result is scalar, okay. And we have theory to support that is a F value, the FML times the sample size follows a chi-square distribution. Okay, the distribution is this number. The P again, P is the number of parameters in this model. I'm sorry, the P is the number of variables in this model. Okay, and the Q is the number of parameters in this model. Okay, the difference is the distribution. Okay. This is the theory part. Now let's look at a very simple case. Simple linear regression. We start from simple linear regression when we have the covariance matrix. Now let's go back to the simple linear regression as our example to check the mean analysis. Okay, to investigate the mean part of SEM. So this is our simple linear regression. Previously, we just don't care about beta zero. We assume the beta zero is zero, and then we look at the covariance part. But now let's consider beta zero here. Beta zero is the intercept. Beta one is the slope. Now we have y outcome, which is dependent variable, and x is our independent variables, okay, predictor. And we have the residual part E. We assume the variance is sigma square. Okay, this is the fixed. So, sigma square is for all I values. Okay, the variance is the same. That is our simple linear regression. Okay, previously, if we assume the mean of y is 0, we don't have any beta 0, okay? Beta 0 is gone in that previous example. Then we have path diagram like this. We have dependent variable y here, we have independent variable here, and we have coefficient from x to y. We assume the slope or the coefficient is beta. So we have coefficient here, and the residual from e to y, we assume the coefficient is always fixed at 1, okay? And we have variance of residual, we have variance of x. So this is our previous path diagram without considering the mean part. But now, and of course we have assumption, okay, so the independent variable x and e residual part are independent. There's no association, no covariance between them. But now, let's look at the mean and covariance SEM. Okay, so we have two parts. So you can see that we have a new symbol here. We have triangle here. What does that mean? Okay, triangle in SEM means, okay, a constant variable. So usually we put a 1 inside of the triangle to see, okay, to indicate that that is a constant. So this is a new part for me. So simple regression can be shown by this path diagram. In addition to the previous part here, okay, we have triangle marked with 1 means constant. And then from 1 to y, we have contribution of intercept. Okay, intercept is a constant. Okay, from constant to y, we have beta 0. This is the beta 0, the coefficient of beta 0. Beta 0 times 1, okay, we have the intercept. And for x, we have variance of x. We also assume the mean of x is not 0. Okay, so we have the mean of x. So from 1 to x, we also assume the mean of x is mx. Okay, so we have mean of x. And the mean of y here. So combine this together, and of course the previous beta 1 here. Combine them together, we have the path diagram, a simple linear regression. So previously, we introduced the 3 methods to get the capital sigma. We have directed algebra calculation, we have tracing method, we have RAM matrix calculation. Okay, so this is our homework 1, this is our homework 2 in SEM 1. But now let's look at the mean. Same thing, okay, we have these 3 methods to do the derivation. So let's look at the first method. So this is a path diagram. For the algebra derivation, we should start from the equation. Remember that in SEM 1, so in homework 1. So we start from the equation of mediation. Okay, so we have mediation equations, 2 equations. And starting from that one, we do the derivation for each element of the capital sigma. Okay. So we have 3 elements in that case, xm, xym, and we calculate the components of that matrix. So for mean part 6, okay, so we need to start from the model equation. Okay, so what is our model equation? We have y here, we have beta 0, we have beta 1, yeah, we have beta 1 times x plus the residual. Start from the model equation, okay, and follow the rules of expectation. So now we are going to look at the mean. So it's expectation, not the covariance. Okay, so previously when we talk about sigma, so we use a covariance matrix. But now it's about mean, so we should look at the expectations of that value. So So if we have really simple case, simple linear regression, then the question is that what is the mean of x? Okay, mean of x. So it's expectation of x. In this case, it's quite simple. So we know that expectation of x is mx, okay, starting from 1 to x. Then we have the mean of x. Or if you really want to add another part, then we have x here, then we have the mx times 1. Okay, so we have x, go back to 1, it's the coefficient here, and then we have 1. 1 is a constant. So two equations. So expectation of x, expectation of this one, a just expectation, okay, of these two, it's just mx. Mx. Mean of y. Now we need to check the mean of y, expectation y. So the equations here, okay, so expectation y, let's just do it here. So expectation y is just expectation of all of this, okay? Beta 0 plus beta 1 times x plus e. And the beta 0 is constant, okay, itself. And the beta 1 is constant, we take it out. And then expectation of x. And then expectation of e. Expectation of e, by our assumption, we assume that the mean of expectation of the residual is the expectation of the residual part is 0. Okay, and then this part we have already obtained from the previous step. Okay, this here. So it is beta 0 plus beta 1 times mx, the mean of x, plus 0. Okay, that's it. This is the mean of y. This is the mean of y. So the algebra. And then the second method, the tracing. You remember we have a lot of like rules. Okay, rule 1, rule 2, we have 2.1, 2.2. We have a lot of rules to calculate the covariance elements. Okay. So we also have some rules for tracing method of mean. Start from the variable interest. Okay, that's one rule, just like the variance part. For the variance tracing rules, we always start from the variable interest. Okay, and then going back through single-headed arrow to triangle. The final point is triangle because it's about mean. Just like the tracing rules for covariance part. Going back through the single-headed arrow to, in that case, for covariance is to another variable, but for mean part is go back to triangle. Multiplying the path coefficient paths, okay? If you have some coefficient path, then just multiply that value. Adding all possible paths together, okay? So if you have multiple paths, then add all components together. So for example, mean of x, let's try to look at the mean of x. Mean of x, here, mean of x. X is a variable of interest, so we start from x. This is our starting point. And then goes back to 1, okay? Going backward, so from 1 to x, there's a path, okay? But now we need to going backward through single-headed arrow to 1. That's it. This is path. This is the only one, okay? Single-headed arrow. We don't have any other single-headed arrow goes to X. So that's it. This is the one component. That's only component. So start from X, going back to 1, multiply the coefficient we just passed. And adding all possible paths. This is only possible path. So mean of X is just mx. That's it. Of course, you can just times 1, but it doesn't matter here. Mean of Y. Mean of Y. Starting from the variable inches. Okay, we start from Y. This is our starting point. Start from Y. Finally, we need to go back to 1. Okay, so here I found the 1 path. Again, backward. Okay, follow backward. Okay, single-headed arrow here. That's one possible way to go back to 1. So this is a coefficient, okay, times the coefficient. That's one possible way to go back to 1. But is there any other possible way? Yes. Okay. You can also follow this road, okay? Backward, single-headed arrow. And then backward, single-headed arrow. Use this path. This is also possible. Go back to 1. And then we have beta 1 coefficient here. We have mx coefficient here. Times, okay, multiplying the path, coefficient path. So this is one possible component, and the other possible component is beta 1 times mx. That's it, okay? Finally, we have 1. This is the other component. So add these two components together. So add them together. We have beta 0 plus beta 1 mx. That's it. This is the same we obtained before. Near 1. Okay. And then we have RAM method by using the matrix. Okay. RAM method. So we also need to figure out some matrix. We have, okay, previously we have F matrix, we have A matrix, we have S matrix for covariance matrix, for covariance, kappa sigma. Now we consider mean, we also need to know an M matrix. Okay, for mean structure, we need to know M vector, not matrix, vector, which include path from 1 to all variables. Okay. If a path exists, then the path coefficient is used. Otherwise, the corresponding element is 1. Okay, so we have 2 variables. We have x and y. So M vector, we have 2 variables. Okay, and then from 1 to x. Okay, from 1 to x. If a path exists, yes. Okay, from 1 to x, the path coefficient is used. Okay, so we have mx here. And from 1 to y, if a path exists, the path coefficient is used. We have 1 to beta 0. Okay. So this is our m. This is our m. And then we use a formula to calculate the mean. Okay, this is our formula. This is our formula. Okay. So we have F field matrix, we have another matrix minus the A matrix. A is a single-headed arrow. Okay, single-headed arrow matrix. We have M vector. Okay, we just do the calculation by following this formula. Okay. So what is A? Okay, A have X here, we have 1 here, we have X here, we have X right here. Single-headed arrow, okay, so from X to X, no, single-headed arrow. From X to Y, yes. So we have beta 1 here. Okay. From Y to X, no. From Y to Y, no. So that's our A matrix. Okay. And another matrix minus A. Okay, another matrix minus A here. Okay. And then inverse. Okay, so inverse. Okay, we do the inverse. And also and the M vector here. Okay. That one is the MX. The calculation. Okay. MX. Here we have MX times beta 1 plus 0. That's it. This is our mean. So we finally the mu is this value. So mu is the mean of X and the mean of Y. So mean of X is just this number, MX, okay? Mean of X is MX. Mean of Y is MX times beta 1 plus beta 0. It's just the same mean of Y we obtained before. Okay, so I'm doing the calculation here because for F is independent variable, another matrix because we have simplified the path diagram. So mean of X here, MX. Mean of Y here is MX times beta 1 plus beta 0. Okay. Just calculated the components by using this formula. Okay. So we have 3 methods, 3 ways to calculate the mean. Okay. Algebra calculation, direct calculation, tracing method, and the RAM matrix calculation. All these 3 methods support the same mean of X, same mean of Y. Okay. Same thing, if you have the mediation model or multiple regression, you can just follow this way, okay? Do the derivation. Same thing. Okay, so let's try to apply the mean structure to a regression, okay, mean structure regression. Suppose we have HVLTT. Remember that HVLTT we have different ways. The original data actually we have 5 ways, but we only need to take two waves and do the regression. Suppose this is a regression. Okay, so from the first wave to the second wave. Okay, so we have HVLTT score, which is a memory test score. We only use 2 variables from the 5 waves of data. So we have 2 waves, use variables. What is the model? We assume this is a regression. Okay, so the second wave depends on the first wave. The first wave inference the second wave of the memory test. This is our model. Okay. Okay, we regress on. And then something new here. Here, look at this part. We have some brackets. Remember when we talk about the keywords of M+, what does that mean? For brackets, what does that mean? Brackets means mean part, okay? We want to look at the mean of HVLTT1. We want to know the mean of HVLTT2. In addition to the various part, I add the brackets. Want to check the mean. So we have the triangle here. We have the mean for HVLTT1. We have the mean for HVLTT2. Of course, we have the decision. This is just a simple linear regression. Okay, not a simple linear regression. So that's our M+ code. So I'm gonna have food. Okay, so I'm gonna upload the food to LC. Okay, so that's it. This is our code and this is our model, simple linear regression, which is simple linear regression. TN plus. So the data set, TN plus. This is the original data set. We have so many weights. We have 5 weights, but I'm gonna use the first 2 columns only, okay? And the first column is an independent variable. The second column is a dependent variable. We assume there's an association between wave 1 and wave 2. Simple linear regression. So that's a code here. And just run. Okay, highlight this model. Let's see. Model result. Okay, model result. Dependent variable HVLTT on HVLTT1. Okay, HVLTT2 on HVLTT1. The coefficient slope is 0.710. Standard error, t ratio, p values. And then here, okay, means, okay, mean of HVLTT1. That is the mean. And this is a beta 0. Okay, this is mx. Remember that in the previous example we have something. This is the independent variable. This is mx. We have the mean of x, and then we have the intercept here, beta 0 here, and we have beta 1 here, coefficient here. This is the mean SEM path. So mean of HVLTT is mx. This is just mx. This is a value here, mx. Intercept of HVLTT2, this value is a beta 0. Okay, this is a beta 0. Intercept. And the coefficient, okay, this is the coefficient beta 1. HVLTT on HVLTT1, this beta 1 is 0.7103. And of course, we have some variance. Okay, we have the variance of HVLTT. This value. There are residual. The residual variance of here. Residual variance 15 point some. That's our main model. Yeah, that's our main model. MX, beta 0, beta 1, variance of independent variable, variance of the residual dependent variable. All of these are reported here. See. That's M plus if you use R. Yeah, Lavan, for example, if you use the Lavan package, then that's our model. Yeah, the original data, library, Lavan. This is our simple linear regression model. So the dependent variable tilde means regressed on. Okay, dependent variable HVLTT2. For Y is regressed on HVLTT1. And both of us in N plus, we use brackets to show I'm gonna look at the mean of these two variables. In Lavant package, we use tilde. Okay, it's reversed on one, it's reversed on one. So that means I'm gonna look at the mean part of this one, mean part of this one. Okay, these two variables. So we use SEM, and this is our model, regression model, the data our HVLTD. And here, this is a key note. Okay, the option, the key option. Mean structure, yes, by default. By default, if you didn't specify anything, the mean structure is not considered. But if you active that, okay, if you put this option available, mean structure equals yes, then it will just do the mean and the covariance analysis together. Okay, we have the summary. So use a hard code. This is a code HVLTD. This is the R code. And starting working directory, you should go to session, okay, choose directory. And read data. You can check the data. Okay? You can check the data by clicking on the head. So that's it. So originally we have 5 ways, but I use the 2 ways. Okay, so this is our model. And the data analysis. So finally, we have the results. Algorithm part. And the regression part. Regression part here. Let's make it 1, let's 2. That's better. So regression coefficient from HVLTD1 to HVLTD2, okay, 0.7, it's the same number, standard error, P value. Intercept, now, okay, we have intercept for HVLTD1, that's it. Intercept for HVLTD2, that's it. This is beta 0, okay. This is MX. Variance for HVLTD1, okay. This is residual variance for HVLTD2, okay. MX here, beta 0 here, beta 1 here, and those 2 variance. Yeah, it's a very simple case to do the data analysis of mean, okay. Oh, I have already prepared those slides. That's it. Okay, so I don't have any homework today, and the next time we will have homework 5. Okay. So next time we will also talk about homework 3 and 4 first, and then we will have homework 5 for growth models. And then we have already done this semester homework. The next part is just the presentation and the post project.
And you're going to update all that on ELC this week or something?
Oh,
the
when
course-
you submit the scores, when you submit the second part. You mean the homework 2?
No, the final project.
Oh,
For
yeah,
April
Okay,
29th.
Okay, yeah, I would do that next week.
Yeah, okay.
Yeah. Okay, any question? Nice. Then that's it. This for today's class. Thank you.